So this time we're going to talk about recurrent neural networks. I'm going to give a brief overview, some of the stuff that was already covered in the reading. And then I'm going to talk about some applications of recurrent neural networks, about some of the things that they can learn, both empirically and theoretically, and also some more advanced modeling techniques using recurrent neural networks. I don't have a huge amount of material this time, so I'm happy to, talk, take questions, expand on things and stuff like that. So feel free to interrupt at any time. Let me get started. So recurrent neural networks, the reason why we want to use them for NLP is because NLP is full of sequential data, or language is full of sequential data. And to give an example of this, we have words in sentences, which is kind of like maybe the more standard thing that you would think about, but also characters in words, or sentences in discourse. So there's all kinds of things where we have smaller units that compose into larger units, all the way up to books or document collections, etc. And there's long distance dependencies between all of these things. So one very common example of this is agreement in number or gender. So he does not have very much confidence in himself versus she does not have very much confidence in herself. And this is just in English, which has a very, very small amount of agreement. It's basically, this is one of the few examples of agreement in gender, and then you have agreement in number between like subjects and verbs, for example. But there's plenty of other languages that have much more necessity to model this agreement syntactically. Things like selectional preferences. So an example like this, where this word here basically is, in my version of English, is pronounced exactly the same way. So if you wanted to talk about the rain has lasted as long as the life of the queen versus the rain has lasted as long as the life of the clouds, you would need to, a speech recognition system would need to handle this long distance information. Does anyone use like Google speech recognition for writing, or any sort of speech recognition for writing emails or things like this? Okay, I do all the time when I'm walking to work or something like this. And it's kind of interesting. You can kind of tell it does a first pass of speech recognition where it's looking only at local information, and then when it finishes up doing speech recognition, it then fixes everything in the sentence. And you can kind of tell it's considering the long distance information after that. So my suspicion, I don't work for Google, so I can't confirm this, but with my knowledge, I'm guessing that probably they have some sort of local language model, like an Ngram language model. Then they have an RNN or long distance language model going and cleaning things up afterwards. So, yeah.
What is the challenge in the first example?
Oh, so the first example, like just to tell, like he does not have very much confidence in herself would be a bad translation, for example. So in Japanese, these are both the same word. There's no gender agreement in the thing. They would both be jibun, for example. So if you wanted to translate this appropriately, you'd have to make sure it coordinates. And it's a much bigger problem when you're translating from English into a language that uses lots of gender and agreement, for example. So like going into Russian, or going into even French or Spanish, you have to have agreements between like nouns and their pronouns and stuff like this. Any other questions? Okay. And there's even more interesting things. These are kind of simpler examples. There's if you think about what is the referent of it here, if you think about co-reference resolution, the trophy would not fit in the brown suitcase because it was too big. What does it refer to here? Trophy. And then we change this to small. Suitcase. Okay. Do people know the name of this sort of problem? Yeah, a Winograd schema, yes. So a Winograd schema is basically something where you need to understand the semantics of the world, and you have two reasonable choices between words. And there's actually something called the Winograd schema challenge. And recently there was a data set called Winagrande, which tried to make this larger, Grande, Winagrande. And Grande is large in Spanish or other languages. So um, I kind of like these problems intuitively because it's kind of hard. It's relatively hard to cheat on them if you have two reasonable choices. So you kind of have to demonstrate understanding in order to get them well. And that would include reasoning over long distance dependencies. So recurrent neural networks, as was also covered in the reading, are basically, they're ways to remember, or if you think about them from this perspective, they're ways to remember information across long distances. And it's essentially as simple as this, where a standard feed-forward network has some sort of context. You transform it to get a vector, and then you use that to predict a label. A recurrent neural network, basically, the definition of it is that you use some sort of vector that you calculated in the previous time step to update your vector for the current time step. And this is in a progressive manner so that you're going from left to right, for example. If you look at the processing sequence, if you unroll it in time, basically you're applying this RNN function, maybe doing some sort of prediction, as you gradually move through the sequence. But importantly, this RNN function is the same at each time step. So you can apply it as many times as you want. Training RNNs, if you're, for example, making a prediction at each time step, then you have labels at each time step. You calculate a loss. Loss 1, loss 2, loss 3, loss 4. And you sum them all together. And now this gives you your final loss, right? So this is a single final loss function. And then you can backprop through this. So despite the, yeah?
Question on the previous slide.
Sure. Oops.
It would be possible to backprop at each step. Why not do that?
So that's a good question. It would be possible to backprop at each step. Why not do that? So why are we summing them all up at the end? Yeah?
Because the loss related to movie will be dependent on the previous one.
The loss related to movie is dependent on the previous one, the previous time step. Well, theoretically, you could backprop through loss 3 before you get to movie and then backprop through loss 4. So why wouldn't you do that? Yeah?
So the weight should not be changed, so the weights are shared across the time step. So we need to finish everything.
The weights should not be changed, so they shouldn't be shared across the time steps. Shouldn't be changed across the time steps. I think that's maybe a good point. The one qualifier to that is backprop and update are different, so you could potentially backprop and then update at the very end. But like if you updated it at every time step, that might change the weights. Any other ideas? Yeah.
The initial weights would be changed much more than the maintenance.
The initial weights would be changed much more than the other ones. Actually, that's still the case in this scenario here. The initial weights get feedback from more loss functions than the final ones, because the final one only gets the feedback from the fourth loss function, but the first gets it from all of them. This is a surprisingly good question. It allows me to clarify lots of things. Yeah.
Adding all the weights like from all the time steps helps to collect the context of the entire
It helps collect the context. That is true, but you actually still would get that if you backpropped individually after each time step as well. And the reason why is because you're backpropping from 4 all the way to 1. So, did you have a hand here? Or? Yeah.
So in this case, we'll actually update each parameter once, so it should be more efficient.
Yes. So that's the reason why. So if you think about it, if you backpropped after each time step, you would have quadratic complexity because you would be backpropping after the first time step and taking, the equivalent of one step back. The second time step, you'd be taking 2 steps back. Third time step, you'd be taking 3. So here, it's linear time in the updates because you're essentially able to backprop from 4 to this vector, then you backprop from 3 to this vector, but you also get the weights from 4, the gradients from 4. So I think that's a big reason why you would want to calculate all of them before doing backprop. But there is a problem with this also. Yes, sir.
So based on the reading, this looks more like a transducer type of architecture, but there was also an acceptor architecture where only the last one is considered.
Yes, and we're gonna talk about that in a second. Yeah. Any other questions? These are good questions. And as I said, I don't have a ton of slides, so happy to accommodate.
I didn't quite understand that by the backprop is different from the update. Like, why would you calculate the backprop?
Oh, sure. So backprop is different from update. This is a nice concept to know. And basically, what the forward algorithm does. Let's first talk about forward. So what the forward algorithm does is it calculates forward through the neural network to calculate all of the values at each of the nodes in the computation graph, eventually culminating in this case in the total loss, which is the final node in the graph. And the total loss is the one that you want to be minimizing, basically, right? What backprop does is it then takes the total loss, it goes backward through the graph, and it calculates the gradients of all of the parameters with respect to the total loss. However, you have now calculated the gradients, and then the next thing that you can do is you can run your SGD optimizer to update the gradients, to update the parameters if you'd like. You don't necessarily have to do that though. And one example of when you wouldn't want to do that is, let's say you want to calculate the gradients over tons and tons of examples. So you want to calculate gradients over 5,000 sentences all at once. But you can't do this because you can't fit 5,000 sentences onto your GPU or your CPU. So what you do is you run forward propagation, backward propagation, and calculate gradients for the first 50 sentences. Then you do the next 50, and you do this over. You do this like 100 times over until you get 5,000 sentences, and then finally you actually update the parameters. The reason why you might want to do this is because stochastic gradient descent, where you update after like every example, can be unstable because you're getting unstable gradients from a single sentence, whereas you'd actually want to predict the gradients over a larger set to get like a stable trajectory through the gradient space. So it's important to know that this like forward algorithm, backward algorithm, and update can be separated, and you might actually want to do forward and backward several times before you can do a gradient. Yeah. Does that answer the question? Okay. Any other ones? Yeah.
So how does this work with the, I'm a little bit curious about the next sentence. This is just one sentence. So like once you do the entire gradient descent for just one sentence and then you move on.
I'm going to talk about this at the very end. Like if you have long sequences, how can you handle these? Any other questions? But for the time being, let's just assume we're doing one sentence at a time. Okay, so I'll move on. So RNN training, I've already kind of talked about this already, so maybe I can just glaze over it. But the unrolled graph is a well-formed directed acyclic graph. So if you think about it, this way, it looks like you have a cycle in the graph. And having a cycle in the graph would be a problem because there's no way to go forward in topological order because there's no topological order to a graph with a cycle in it. But the unrolled graph itself, you'll notice there's no cycles here. It's directed starting from the left, going all the way down to the bottom. So what we can do is we can just do normal backpropagation. We can calculate all the way to the end, calculate the sum of the losses, and then these get backpropagated backwards. But because the parameters are tied across time, the derivatives are aggregated across all time steps. And this is called backpropagation through time. But basically, what I mean by this is the same parameters are used to calculate all of these RNN updates. So you can almost see, like, if I wrote it on the board, actually maybe I should have written this on the slide just to be clear. But we have RNN, RNN, RNN. And going into these RNN updates is not just the inputs in the hidden states, but also we have a weight matrix or weight matrices that are influencing these RNN functions. So we just backpropagate into the weight matrix, and the weight matrix, the update to the weight matrix, just becomes the sum of all of the gradients that come back into it. Is this clear? Yeah. Okay. So this is kind of the high-level overview. There's a bunch of different varieties of recurrent neural networks, which I'll be talking about later. But now I'm going to move on to the thing that was also briefly covered in the reading, which is what kind of RNNs are there. And there's a bunch of different things they can do. I say represent a sentence. It could be represent a text sequence. So read a whole sentence, make a prediction. Represent a particular context within a sentence. So read the context up until that point. So if you're talking about representing sentences, basically this is the acceptor that was mentioned in the reading. So you read the whole sentence, and then at the very end you predict. And this can be used for things like sentence classification. It can be used for things like condition generation and retrieval. So sentence classification, we've already talked about it a lot. Condition generation, we're going to talk about it next time. So that's basically where you encode some sort of context, and then you want to generate sentences based on this context. You can also use it for things like retrieval. So like a famous example, I guess they didn't use RNNs there, but it's a similar example. But a famous example is web search. So you have a document, or you have a whole bunch of documents that you want to search over. So you encode all of the documents as vectors. Then you have a query. So you have a different RNN that encodes queries, and you try to basically fit them into the same space so that things that are close in the query space and close in the document space are good, like documents answering that query. And when you do something like this, basically what you do is you have your big document database, which is represented as a big matrix. And then you have your vector here, and you just try to find the nearest neighbor within this document database for this vector. And if you're doing this on a small scale, you just run NumPy, you multiply the vector by the matrix, and you get the argmax, and you're done. But if you want to do this for very large scale data, like millions and millions of vectors, there are libraries like, there's a library called FAISS that allows you to do these queries very, very efficiently. Another thing that you can do is you can represent contexts within a sentence, and this is for things like tagging. I believe the tutorial that Pengcheng is going to do pretty soon is going to be covering named entity recognition. I think with recurrent networks, right? So we'll have an example of this if you want to go to the tutorial, which he'll be publicizing soon. And this can be done for things like tagging. It also can be done for things like language modeling. So if you think of language modeling as a tagging problem where your tag is the next word in the sequence, you can do that as well. And it can also be used for calculating representations for any sort of downstream task if you want. So an example of a language model, you have your RNN, and you predict the next word. You have your RNN, you predict the next word, RNN, predict the next word, RNN, predict the next word, etc. Are there any questions so far for this? Yeah.
Our point in get the application and the information retrieval part.
Okay. So yeah, so for information retrieval, basically, like let's say you want to find documents that are relevant to a query. So like let's say you wrote deep learning for natural language processing, and of course, you know this class is the most relevant material you could possibly have. So you want to find this class on this website. I'm joking. Yeah, there's lots of good material. I hate when I tell a joke and nobody laughs. I don't know. I don't know if it didn't come across or it just wasn't funny at all. Yeah, so like but if I said deep learning for natural language processing and the name of this class was neural nets for NLP, that's not a trivial matching, right? You need to know that neural nets, neural nets is an equivalent or a synonym for deep learning, and natural language processing is a synonym for NLP. So basically, what the RNN would do is it would encode each of the words in the query into a vector, where synonyms would be encoded into a similar space, and you would just hope it would be able to learn it. I wasn't planning on covering this really extensively, but the way you can train things like this is you can take a query and a bunch of candidate documents. You encode 50 candidate documents in the query, and you try to make sure that the score of the correct document is higher than the score of all the other ones. And that would be like a loss function that you would use there. Any other questions? Okay. So another really popular thing to do, especially for tagging, is bi-directional RNNs. And it's a simple extension. You just run it in both directions, concatenate them, and predict a tag. So for example, this is an example of part-of-speech tagging. And the advantage of this is you have the left context, you have the right context. So if the context that you need to determine that this is a verb is on the right side, then you can use that as well. Okay. This can't be used for language modeling. And the reason why is because, anybody? Yeah.
It requires both directions instead of just going from beginning onward.
Could you say that again? Sorry.
Like when you're language modeling, it's kind of like given the previous words, what's the next word?
Yeah.
As opposed to going in both directions.
Right. So yeah, the formulation for language modeling is based on the chain rule, and so in order to do this, you can't condition on something that you need to predict in the future. You can only condition on things that you have predicted in the past. So if you're also looking at your right side, then basically you're cheating. You're making your task too easy. Also on kind of a more practical level, like let's say you then wanted to use your language model to generate text. There's no way you could do that by encoding the right side text with a right to left language model because you don't know that text yet. So, so yeah. So you can use it for things like tagging, but cannot use it for things like language modeling. Or at least in the most standard version of language modeling. There are some weird exceptions. So we have a code example for this, and as I mentioned, that Pengcheng will do a tutorial. Okay. So vanishing gradients. So like as I mentioned, one of the big advantages of recurrent neural networks is they theoretically allow you to handle long distance context. They actually theoretically allow you to handle infinitely long context in linear time. So like you can keep as much information around as you want, and it will only be linear in the length of processing your sequence. This is in contrast to things like transformers, which we're going to be talking about later, or attention-based models, which are quadratic. They don't require super linear time to take into account long distance context. But one problem with RNNs is vanishing gradients. Basically the problem is if you have an RNN where at each point it is modifying the hidden input, the gradient will change between this point and this point, right? And specifically, if you're using something like a tan-h function as a hidden activation, this is kind of like the standard activation you use. The tan-h function is 1 and -1. And if you look at the gradient of the tan-h function, around 0, the gradient is, wait, tan-h is 1 or 0.5? It's 0. What's the gradient of tan-h? I forget. One.
Oh, 1.
1. Okay, it's 1. Yeah, so that's what I thought. The sigmoid is 0.5, I guess. So that's why. So the gradient here is 1. So anywhere except when the input is exactly 0, your gradient is going to be less than 1. And if you multiply this in over and over and over again, it's not exactly that simple, but like if you multiply this in over and over and over again, it's going to decrease as you take time steps back. So you multiply by something less than 1, then you multiply by something less than 1 again, you do it again, and if you keep on doing this, gradually the gradient signal that you get from the output is going to get less and less and eventually disappear. Not disappear completely, but become very small. The reason why I said it's not as simple is because you're also like multiplying weight matrices, you're adding biases, stuff like this. But overall, you have 2 options. One option is that your gradient gets smaller and smaller and smaller. The other option is that your gradient gets bigger and bigger and bigger. And both of these are kind of bad. You know, if you have these really huge gradients, that becomes unstable. Really huge gradients are a little bit easier to deal with because what you can do is you can just clip the gradient and renormalize it. So if you have a gradient that's greater, where like the sum of the gradients or the sum of the absolute value of the gradients is greater than 5 or something, you can renormalize so that the absolute value of the gradients is limited to 5. This is a very common thing to do called gradient clipping. But if your gradients get smaller and smaller and smaller, then you're just kind of out of luck. You have no signal as you get to the earlier parts of the sentence. This is particularly a problem for things trained as like this, for things trained as acceptors. So you wait all the way to the end of the sentence, you get your signal, and then you backpropagate back. And you get virtually no you get virtually no gradient at the beginning of the sentence or anywhere that's very far away from this. Yeah.
So I wonder what happens if we use a value where the gradient is 1 or 0.
Mm-hmm.
So if it's 1, then it's backpropagate for a long distance.
Mm-hmm.
But I can't see what would happen if the gradient is 0 somewhere.
So what happens if you use a ReLU? I think the answer is that would be better than a tan-h, but you're still getting 0 half the time, right? So if you think about it as a random process, that would be like you would lose half of your nodes in the first thing, then you'd lose another half, so you'd have a quarter, then you'd have an eighth, a 16th, etc. So if it was just kind of randomly reordering the nodes after every time, then you would still have a vanishing gradient problem. And actually, the LSTM fixes this, and I'll explain that in a second. So the LSTM is very widely used in NLP, and basically the idea is you want additive connections between time steps. So the reason why you want an additive connection is because there's basically exactly one type of function that will never change your gradient, and that is the identity function. It's the function that won't, it's a function that will not change your gradient regardless of what your input is. addition is addition of the thing with the previous time step with some sort of modification is also similar. You have a identity connection between the previous time step and the next time step. But what LSTM does is it gives you the ability to change values, but also has this additive connection. So what it looks like here is this. And the LSTM has two varieties of hidden states. One is called the cell state, and it's mentioned as C. The other one is the hidden state H. And the hidden state H is something that you're allowed to modify a lot. You're allowed to mess around with it. The specific ways you do this are through gating functions and tanh nonlinearities. So first you run this H through a tanh nonlinearity. Then you have a gating function where you do an element-wise multiply with the sigmoid. Then you have an output function where you do an element-wise multiply with the sigmoid and the tanh. So basically this H changes a lot. It changes even more than a regular recurrent network. But the C, the cell state here, is basically simply the previous cell state added together with a modification that's calculated through the input and this hidden state here. So the really important thing is basically the cell state is carried over and never modified in a nonlinear way throughout the entire update process. And because of this, the gradient flow here will continue to flow back all the way from the end of the sequence to the beginning of the sequence without any sort of mismodification. So are there any questions with respect to this? To give an example, like let's say, I'll give an example later, like of this, but let's say we wanted a LSTM that counted words in a sequence. So a really simple way to create an LSTM that counted words in a sequence is you take this, one of the nodes, you take one node of this, you set this tanh to 1 all the time. That's pretty easy to do, right? You just make its bias term very, very large and it will be 1 all the time. Then you take the sigmoid and you also set its bias term to be very large. So this is 1 every single time. So then you start out with a cell state of 0, and then you just add 1 to it every time step you take. So now the LSTM can count the number of words that you've seen so far. It can have that additive connection, but maybe you also want to count the number of positive sentiment words. So you want to count the number of positive sentiment words, you want to count the number of negative sentiment words. So instead, you set this gate here to identify positive sentiment words. And every time you see a positive sentiment word, you turn that gate on. And so it will increment that every time you see a positive sentiment word. And that gradient will flow all the way back from the end. So like theoretically, no matter where the positive sentiment word occurred in the sentence, you would still be able to identify it and count it. Is this clear? Are there any questions? Or? Okay. So we have some code examples of this as well. So there's some interesting results that look at what recurrent neural networks learn, or theoretically what they can learn. So a really nice paper called Visualizing and Understanding Recurrent Networks examines this. I'm sorry, this is a little bit small on the slides here, but you can either look at the slides on your own thing or click through to the paper. And basically this visualizes the value of an individual node as you run it over characters in a sequence. And one example of a cell state that a model trained to do character level language modeling learned is basically it starts out positive, then gradually turns negative as you get closer to the end of the sentence. And you can see it's not just counting characters, it's kind of like identifying that you're getting closer to the end of the sentence, because if it was just counting characters, it'd be the same color no matter what sentence it was. So you can see that it's kind of gradually identifying the end of the sentence. Another example is one that turns on inside of quotes. So you have a quote here, then once you see the quote, the cell is on for the entirety of the quote. Then you get a close quote, and then the cell turns off. And then you get another quote, and the cell turns on again. So why would this be interesting? You know, in books, in novels, people tend to say different things in quotes than you get outside of quotes. Like, for example, they tend to use the first person more often. They also ran this on code, so you can see this is turning on in if statements. Importantly, not all of them are interpretable. So, you know, some of them are you can't really tell what they're doing, but remember the language model also has to learn how to spell words, for example. And in order to spell words, you might need some cells that aren't necessarily like any sort of interpretable meaning. So any questions about this? One thing yeah, sorry, go ahead.
Is it also possible that some of the cells don't learn anything at all, and probably that's why they're not interpretable?
Is there any chance that some of the cells don't learn anything at all, and that's why they're not interpretable? I'd say, yeah, definitely yes. There are interesting results on recurrent neural network models where you can basically train up a model and then remove part of the model, and it still does perfectly fine. So that's a strong indication that there are some parts of the model that aren't really learning anything. So that's definitely the case. I actually hadn't thought about that in the context of this, but that's a very good point. Any other questions? Yeah.
This goes back to a little bit to previous stuff.
Yeah.
If the LSTM or these kind of gated models are to prevent the vanishing gradient,
Yep.
why wouldn't we just add like a residual connection, perhaps like temporally between one time to the dog?
So that's a good question. So residual connections are additive connections between cells, basically. Additive connections between neural network layers, and they're very widely used in vision, going from like the early layers until the end. I think an LSTM is a residual connection between time steps, basically. They already did. This is the reason why, perhaps. Maybe your question could be reinterpreted into why did we add extra complexity, like all of these gating functions and stuff like this? I think the reason why is essentially, this is kind of like one neural network layer, right? It's a neural network layer where we have a regular NLP layer, and then we have a gating function. And we're adding that in here. Then we have another neural network layer and a gating function, and we take it out. So if you think of it, it's like ResNet through time in that way. So, cool. Any other questions? Yeah.
So the reading said that there are multiple multiplications due to which gradient vanishes. So which part of this exactly is preventing that multiple multiplication?
The cell having no, you see this path here on the top? Yeah. There's no multiplications anywhere in this path. So between the previous cell state and the next cell state, nothing is ever being multiplied. It's completely additive. Yeah.
I saw in the textbook that there's actually a forget gate which multiplies on.
Yeah, so that's an interesting question. So where's the forget gate in this diagram? And the answer is the forget gate wasn't proposed in the original LSTM paper. It was proposed in a later paper called Learning to Forget. So this is the original LSTM. But where the forget gate occurs is basically here, I think. I haven't looked at LSTM. I haven't looked at LSTM code in like 4 or 5 years. The forget gate is here, I think, right?
It's on the left side.
It's on the left side. Okay. Basically, that is adding a gating function between here and in the next one, and that is a multiplicative connection, right? So actually that kind of weakens the argument for LSTMs as being a really good model because it's adding this multiplicative connection and it's potentially causing gradient vanishing to occur. The way you prevent that is by initializing the forget gate so that it almost never forgets anything at the very beginning of training, and it only learns how to forget things later in training. So at least by the time you start using the forget gate, it doesn't it's already learned enough that it can decide where it should be for getting these gradients. Yeah.
I have one more question on the next slide.
Mm-hmm.
So it looks like the hidden state should be more localized than the self state.
Uh-huh.
But right now it's showing that the self state is able to picking up like all these localized features, quote, or if argument.
Mm-hmm.
So I wonder, like, what would happen if we were visualizing hidden state?
So that's a good question. So like, what would happen if you visualize the hidden state? You mentioned it should be more localized. I'm not exactly sure what you mean by localized.
So
but
if
like,
you look at the figure, the paragraph, like quote is a localized feature. Like, it has nothing to do with the context. So it should be picked up more precisely by the hidden state other than self state, where self state is more like generalized contextual information.
Yeah, so that's a good question. So like when you say localized, the definition of localized, just because people in the back can't hear, I'll repeat everything. But a quote appearing seems like a local feature. Like it's one that you can identify from just the local context, whereas what we were showing there was that the cell states were actually had kind of a more interpretable explanation. And I wonder what would happen if you visualize the hidden states. I think that's a really interesting question. I actually don't think these cell states are showing local features, but rather they're showing kind of global-ish features, right? So like we are inside a quote. It's not we have identified a quote mark, but we are inside a quote. And that seems like a kind of global contextual feature that you need to have long distance things about. So it could be very possible that if you looked at the hidden state corresponding to the cell state might be identifying a quote, like the actual quote mark, and then the cell state resulting from that would be showing the result of that identification and changing in a more global way. So, yeah, any other questions? Yeah. Uh-huh.
We just clip and renormalize like we do for exploding.
Couldn't you clip and renormalize just like you do for exploding gradients? I think the answer to that is probably no, and the reason why is because with exploding gradients, basically you are taking a really huge gradient that would destabilize your training and you're reducing it to a reasonable size. For the vanishing gradient problem, the bigger problem is that you're only learning to backprop a few steps, right? So because you're only learning to backprop a few steps, like 1 or 2 steps, you're losing information about global relationships between words. So like if you had a very high positive sentiment word at the very beginning of the sentence, but you weren't predicting the tag until the very end, the gradient would never flow back all the way to the beginning of the sentence and tell you, yes, this is a very high positive sentiment word. It's not that you don't have any gradients at all. It's just that the gradients are only flowing back a few steps. So if you tried to do any sort of renormalization, you would basically renormalize so that the few words that did get gradient still had gradient, but the words that didn't have gradient still didn't have gradient. So that makes it harder to handle than the exploding gradient problem. Okay, I'll move on a little bit. So here are some other interesting examples. So this is an example of an LSTM that can learn the length of the sentence. This is specifically an encoder-decoder model, so a model that reads in an input and tries to generate an output. And during the encoding step, there are some units in the LSTM that gradually decrease. And then you get to the decoding step, and it gradually increases. And this is for machine translation in particular. And the interesting thing is in machine translation, your output's generally the same length as the input. So it kind of is rational to count the number of words in the input and not finish generating output until you've generated the appropriate number of words in the output. So you can tell there's basically a single cell or two cells that are trying to do that for you in the learned LSTM. This was not supervised in any way. The fact that this happened was just discovered by the model, basically. Notably, this is difficult to do for other varieties of gated architectures. So this is difficult to do for GRUs, which I'm going to be talking about later. So you can keep this example in mind. Another impressive result is that people or researchers trained a large language model on character level language model, I think, maybe word level, character level, yeah. So they trained a large character level language model on lots of Amazon reviews, and then they analyzed the outputs and found there was, as little as a single neuron in the LSTM that learned something as complex as sentiment. So basically, whether this is a positive review or a negative review. In a way, if you think about this result here, where it learned whether you're in quotes or not in quotes, actually perhaps this is not super surprising. And the reason why is because if you're saying bad things about a movie, you're very likely to continue saying bad things about a movie, right? If you're saying good things about a movie, you're very likely to continue saying good things about a movie. So keeping track of the general sentiment is a very good way to improve your predictive performance. But still, it's a kind of nice result. Sentiment is something that intuitively people care about a lot, and it just emerged without any supervised learning here. So this will be a very good example to think about when we talk more about like pre-trained models like BERT or Elmo or whatever as well. Okay. Another thing is I talked about what do neural networks learn empirically when you train them on language data. Another interesting thing to think about is what can recurrent neural networks learn, or what can recurrent neural networks express? And the answer is anything. So a recurrent neural network with real weights, like the standard recurrent neural networks we use, can be proven to have the expressivity of a Turing machine. And as you know from your CS classes, a Turing machine can calculate any arbitrary function. So a recurrent neural network with the appropriate size, with the appropriate like shape and everything like this can calculate arbitrary functions. So again, this is an example of if somebody tells you a neural network can't do it, then they're lying. Okay. Next I'm going to talk a little bit about efficiency tricks. So we talked about mini batching before in the context of like feed-forward neural networks. This is something that's important in recurrent neural networks as well. And mini batching makes things much faster. But unfortunately, it's harder than in recurrent neural networks because each word depends on the previous word. And sequences are of various lengths. So this is kind of one of the difficulties that you face in NLP, kind of essentially, if you try to incorporate neural network models. So there's a couple ways you could do this. One way you could do this is say, I'm only going to process sentences of the same length within a mini batch. That's one way to do it, and then you get sentences of the same length every time. They have all exactly the same computation graphs, so you can just batch them together. But unfortunately, this breaks down very quickly. So like, for example, let's say you want to train a model that has an input sentence and an output sentence. It's going to be very rare, or it's going to be somewhat unusual to have all of the input sentence and output sentences have the same length. So then you're going to start losing the ability to do so. So what we do instead are things called padding and masking. So padding, basically what this does is it takes the longest sentence in your batch and adds arbitrary tokens to the end of it. You can then run your neural network over this like they were all the same length. And then at the very end, you take a mask and this mask, basically what it does is it zeroes out the values that you do not, zeroes out the values that are not actual values, but rather padded values. And by doing this, this allows you to handle the problems of inputs being different sizes. Fortunately, many toolkits have capacity to do this kind of built into them because it's an important thing to do that you need to do often. So, like PyTorch has what's it, packed sequence or packed sequence, yeah. Something called packed sequence that allows you to pack things, and many of the component functions already consider this and will do padding and masking for you automatically, so you don't need to do it yourself. Usually it's implemented in an efficient way because this is something that's really important. The disadvantage is that anytime you want to do something that's a little bit different than what is already implemented, you're kind of on your own and you're going to have to figure out how to do it yourself. So this is something you're going to have to think of how to do. There are easy examples of doing it, like let's say you just want to mask out loss functions. So then you just multiply all the loss functions that you want to mask out by 0 and all the ones you don't want to mask out by 1. It starts to get a little bit harder when you have like a bidirectional recurrent neural network. So when you have a bidirectional recurrent neural network, you want to do an update on the word example, but you don't want to do an update on this end of sentence symbol because this isn't, or you want to do, or let's say you want to do an update on this end of sentence symbol, but you don't want to do it on this one because this is a padded symbol, so you don't want to update according to it. So it gets a little bit trickier, and I'll just leave it at that. If you have any questions, you can ask the TAs or me at office hours, and we can help. Yeah. Another thing is when you're doing things like padding or masking, what you definitely don't want to do is you don't want to have a 200-word sentence grouped together with a whole bunch of one-word sentences. And the reason why is because if you have a 200-word sentence that goes all the way to the end of here, and then you have a whole bunch of one-word sentences in the same batch, you're going to be wasting a huge amount of computation when you're padding and masking out all of these things here. So a standard practice here is to do bucketing and maybe sort bucketing. So what this entails specifically is you can sort sentences. So similarly linked sentences are in the same batch. So all your long sentences become in the same batch, all your shorter sentences become in the same batch. And this greatly improves efficiency. It removes wasted time and memory and stuff like this. So we have an example of this as well. Yes?
So when you're bucketing, you're going to be kind of decreasing how random the samples are. This is just not really cause a problem in practice.
So when you're bucketing, you're going to be decreasing the how random the samples are. And does that have an impact in practice? And actually, the answer is yes. I glazed over that and I don't have it in my slides, but there is a paper written coincidentally by one of my students. Called an empirical study of mini-batch creation strategies for NMT. And we compare sorting we compared like random shuffling, which is blue, in the blue, sorting by the source only, which is in the green, sorting by the target, which is in the orange, and then source and then target, target then source. And you can see that this does actually have a significant effect on the outputs. It also is interdependent with what optimizer you're using. So if you're using a stochastic gradient, an adaptive gradient optimizer like Atom, the effect is larger. So it is something to be aware of. Nonetheless, I think it's still pretty standard practice to do it anyway. So yeah, there's that. Unfortunately, like a lot of things in neural networks, the answer to this one is not easy, so it's just something to be aware of. That's a good question, though. Are there any other questions? Okay. So another thing that is very, very useful is if you are implementing LSTMs or other varieties of recurrent networks, they can be slow. And the reason why they're slow is they can be slow on GPUs in particular. And one reason why they're slow is because what GPUs like is they like to do one big operation. But if you have a recurrent neural network, you're calling many different small operations, one for every time step, basically. So you can kind of see this here. This is this green part is like preparation. Basically, it's calculating all of the inputs to the LSTM. But then each of these operations here is basically a single time step, and you can see that doing each of these, you have some time waiting, and then you have some time calculating on the GPU. You have some time waiting while you're waiting for information to communicate, and this can slow things down a lot. So people at like NVIDIA or other places have implemented extremely fast versions of standard networks where basically you dispatch it once to the GPU and it calculates the whole sequence using for loops and things like this. So this is very good. The downside is you have a significant loss of flexibility. So like let's say you want to try the LSTM without a forget gate. You're probably out of luck because NVIDIA engineers have not implemented this. Or let's say you want to try your like slightly different variety of the LSTM where you add some interesting thing. Now you're out of luck again because there's no way to do this. It comes with a trade-off. Final thing you can do, you can learn how to program CUDA. I have done this. I will not recommend it for everybody in this room. I'll recommend it for people who are really, really interested in training things, doing like flexible things quickly, but it can be kind of painful to do. But anyway, cuDNN is the library that's used for these kind of things, and this is used by standard by a lot of neural network libraries as well. Okay, so now I'm going to move on quickly to some variants of RNNs that are interesting. So a famous one is gated recurrent units. This is a simpler version of RNNs that preserve the additive connection. And basically what it is you have a gate that either adds your previous value with basically a multiplicative factor of 1 minus ZT, or uses the update with a nonlinearity with a factor of ZT. So basically you get to choose either or which one of the two do I want. So the advantage of this is it only has one hidden state. So unlike the LSTM, which had multiple hidden states, you only have one. The disadvantage of this is you can't do things like counting. And the reason why you can't do things like counting is because every time you do an update, you are forgetting the stuff that you had before. So the scale of this HT is basically between 0 and 1 all the time. So you lose some power by moving to the simpler architecture. So there's many different types of LSTMs. Sorry, there's actually two things here. So one is that LSTMs have kind of a interesting shape. They have a forget gate, they have an update gate, they have various things like this. Why should we use the LSTM as opposed to something that didn't have the update gate, or instead of something that didn't squash the values between 0 and 1 for the input? And this paper by Greffin et al., basically they turned on and off various features of the LSTM. And this allowed you to, and they tested, and it turns out the original LSTM with the forget gate is pretty good. So there was a reason why people use this in the first place. But another thing that you can do is you can do something that's kind of like a mix between the LSTM and the GRU, which ties the input gate and the forget gate. So if you input things, you can forget them as well. And of course, that will also lose the ability to count, but it reduces the parameters somewhat and may be easier to learn. And then if you want to go even crazier, and you have lots and lots of computers to compute on, one other thing that you can do is you can randomly or semi-randomly generate a whole bunch of different types of architectures and see which one does better for your task. And that's what the second paper does. It's neural architecture search. And it essentially takes your input, your previous state, and your previous cell state, and it adds random functions into these until you get the best possible architecture for whatever task. And this is the architecture that they eventually found. I actually have never been able to figure out why you even need identity as one of the things that you can search over, but hey, take it as you will. And you can see that it's kind of like adding together a tan-H, a max pooled tan-H over the hidden state. It's adding in another max over the hidden state. It's doing an element-wise multiply, and then you get the cell. It's doing a bunch of other stuff I'm not even going to try to explain. But it turned out this architecture works relatively well. And maybe you don't care. Maybe you don't care how the computer found this architecture as long as it solves your problem. So there's also interesting modifications to this, like differentiable architecture search that turn this process of randomly like generating architectures into a differentiable process, so you can actually backprop through that process of creating the architecture. But practically, I don't think anybody actually uses this architecture anymore, but it's kind of an interesting, variety of learning or meta-learning where you can figure out which architecture you should be using by just randomly, generating them. Okay. Oh, one thing I should mention though is this doesn't solve all of your problems because you need to define your search space, right? And if the search space for your architecture doesn't include something intuitive and useful, then obviously it will never find this thing. So people are still doing architecture engineering because you need to define your search space in the first place. You need to whittle down the types of things that intuitively make sense, because otherwise just random search or random hill climbing will not find these things. So some other examples of architectures that are widely used. Another one is a multi-scale RNN or pyramidal RNN. I'm only showing the pyramidal RNN here, but the pyramidal RNN is basically like a CNN with stride. So we talked about CNNs with stride last time, where you skip over multiple some inputs. The pyramidal RNN is exactly like that. So instead of every time inputting, so like in the first layer you input all of the inputs. The second layer you input the number 1 and number 2 to the first time step. Number 3 and number 4 to the second time step, number 5 and number 6 to the third time step, etc. And you gradually progress through layers until you reduce the length of the sequence. And this is very widely used in things like character level language modeling, or speech processing, or things like this, where you have a very long sequence at the beginning. Another example of this is like you could encode a single sentence into a hidden vector, and each single sentence would become a hidden vector, and then you have a RNN that reads in the vector for each sentence. And you could even do this, like one hidden vector for each word that you calculate from the characters, one hidden vector for each sentence that you calculate from the words, and then one hidden vector for a document that you calculate by stepping over each sentence of the document. Yeah?
So how do we combine the outputs from the first layer to create the first unit and the second layer?
So the very simplest way is just concatenate them. So you concatenate the two inputs, you multiply them by a weight matrix. And there's probably other ways you could do that, but I think that's the most common way. Yeah.
So one advantage of doing this thing is like the whole sentence will be summarized into one vector. So in the normal case when it's not hierarchical or pyramidal, can't we do something like pooling in CNNs?
Yes, you could definitely do pooling, something like pooling in CNNs as well. This is concatenation. You could also do, max pooling or whatever. But this concatenation.
No, I meant like with just one layer, not the hierarchical structure, just one layer.
Oh yes, yeah, you could definitely do that as well. It actually I should mention for sentence classification or things like this, it's very often better to do max pooling, even when you're using RNNs, than to use the final RNN hidden state. And the reason why is because it helps gradient flow also. So it will let the gradient flow directly back to the places where you identified the features, as opposed to having to wait all the way to the end of the sentence. And even with LSTMs still sometimes have trouble maintaining information over long distances. Yes?
So how would this be more beneficial than, say, doing something basic like just reducing the dimensionality of each unit by half? So, end of the day, like if we want the same amount of complexity or so we can reduce each unit's dimensionality by half, like per iteration. At the end of the day, like the sparsity overall would remain the same if every unit dimensionality was reduced by half. Instead of combining two units and making it into one, that is of n dimensions, why not just take one unit and make its dimensionality like a half, as in like the subsequent layers?
That's a good question. I think this is strictly more expressive than that. And
because ideally it is also encoding the past information. Given that an LSTM unit already holds the past information, there is no need to combine two together because it is almost safe to say that the second unit will have more or less a lot of information about the first unit and so on.
yeah, I think that's an interesting question. I think this is strictly more expressive than this. And I think basically what you are proposing is something that looks very similar to this, except you zero out some of the weights in the weight matrix. So maybe you can think about like what your procedure would sound like, what your procedure would look like, and if you zeroed out some of the weights in the weight matrix for this, could you achieve the same thing? And I think the answer is probably yes. And if that's the case, then this would be strictly more expressive because you're not zeroing out the weights in the weight matrix. So I'll leave that as homework because we only have 2 minutes left, but I think it's a good question. So there's also, in terms of hierarchical structure, there's also ways, maybe this is a little bit related to what you just mentioned, but there's also ways to express this hierarchical structure in a soft way. This is an example from a paper called Ordered Neurons. There are other examples of this as well. But basically what it does is it has a forget gate, where the forget gate forgets all of the things below a certain point in the, or kind of in a soft manner, forgets all of the things below a certain point in the vector. And so the idea being that at some points in the sequence, you can forget most of the information that you're remembering. In some points in the sequence, you can forget a very small amount of information. And the idea being that some of the information you'll definitely want to remember throughout the entire sentence, like what is the topic of the sentence, maybe what is the subject of the sentence, but other pieces of information you only really need very locally. Like, for example, as a previous word I saw the or that might not be relevant anymore once you've seen the noun, for example. So This is a kind of interesting, an interesting paper, and they show how this could be used to induce structure over the inputs to some extent. If this sounds interesting, there's lots of interesting discussion regarding whether this actually does allow you to induce structure well, and I'd be happy to talk about that, but this is another interesting paper from recently. Oh, yes, and sorry, this is one more important thing, implementation details. So let's say we want to model whole Wikipedia articles. But Wikipedia articles have 10,000 words in them. So we can't fit all of this in memory. So how could we do this? And a very common way to do this is by basically doing something called truncated backpropagation through time, where you run over a fixed length sequence, like let's say 256 words or 128 words or however many words you could fit into your GPU memory. And then you take this and you pass the hidden state only and calculate the next words. So what this is doing is it's still maintaining the information that you had when you viewed the end of the sentence, but it's not backpropping into the previous sentence. And the reason why this is good is the moment you keep this state, you can delete the rest of this computation graph and still fit everything into memory. So this is a very common thing to do and worth knowing. So yes, that's all I have for today. And I'm happy to take individual questions afterwards.